So what we're going to do is summarize all the aromatic reactions we have learned so far. So in the first three examples, we have bromination using some catalyst. Now, when we brominate benzene, we're going to look at the most activated positions, the most likely position for the bromine to go. Now, when you have an electron donator, like a methyl group, we're going to go to the ortho and the para position. So what is that? Well, the ortho positions are right here, and the para position is right there. So if we put the bromine over there, our product will look something like this, where we have our benzene ring, our methyl, and then we just have our bromine either at the ortho position or the para position. Well, with just a methyl group, we can have it at the ortho position. I'm just going to pick that one, although both products are valid. So I'm just going to say plus para. Now, in this second situation, it's the same thing, but now we have two electron donating groups. We have an ether and we have a methyl. Now, which one is the better electron donating group? Well, we know that the ether is the better electron donator. It has free lone pairs, which the methyl does not. So this one will dominate in which position it will go to. So with the ether, we know that the positions that it likes is the ortho and the para position. So this position is empty, is full, so we only have these two positions. So I'm going to pick this position right here simply because it's less sterically hindered. We have less groups next to it, so I'll like to have that. So we're going to have our benzene ring again with our ether at the top, our methyl right here, and I'm just going to write our bromine in the para position. Although ortho position is still valid, however, I'm just going to write the para position because of steric hindrance. Now, in this third example right here, what do we have? Well, it's the same scenario, but now we have electron donator and an electron withdrawing group, which is a nitrate group. Now, electron withdrawing groups, like nitrates, are meta-allowing or meta-directing. So they want the meta positions. And methyl, we already know it's ortho-para directing. Now, the meta position in this situation is this one, and this position is full, while the ortho and para positions are every other position. Now, since they don't agree, we have to go to the same situation. Which one is more electron donating? So that way we can figure out which one will dominate the situation. Now, methyl groups are obviously more electron donating than this electron withdrawing group, so they will dominate the situation. They will tell us where the bromine will go. So the bromine will either go to this ortho position, this para position, or this other ortho position and this para position. Now, I'm going to say that this position is unlikely because we have two groups around it, and that will basically cause steric hindrance. So you'll either go here or there. So I'm just going to pick this group right here since the methyl is smaller than the nitrate, but both positions are valid. And so our group will look like something like this with our methyl right here, our nitrate right there, the benzene ring, and then we have our bromine on this group right here. Now, what about these next two situations? In these next two situations, we have something a little different. We have nitric acid and sulfuric acid. What that means is that we're going to mononitrate this benzene ring when you see these two reagents together. Now, we have the same situation. We have our ether, which is ortho and para directing, and we have our bromine, which is actually a halogen. Even though it's electron withdrawing, it's also ortho and para directing. That's the one exception with halogens. Even though they're electron withdrawing, they're ortho and para directing. So the ortho and para positions for the bromine are these two positions, while the ortho and para positions for the ether are these two positions. So since the ether is the better electron donator, we're going to pick the ether positions, or the ortho positions with regards to the ether. So I'm just going to pick one of them and put a nitrate group on there. So what it will look like is this. We have our benzene ring, we have our ether, we have our bromine right here, and we're going to have our nitrate like this, NO2. Now what about this next example? Well, even though it looks funky, it's not that bad actually. We have two rings, right? And we're going to add a sulfur trioxide to it. Now, which ring will we add it to? On this side or on this side? We're going to look at the more activated ring. And the more activated ring is the one that has electron donating groups. And so this will be this benzene ring, which is more activated. It has this ether to it. So we're just going to look at the ortho and para positions for this ether. And that'll be this position and this position. This is ortho and this is para. Now, we also notice that this group right here also supports this ortho position and also this para position. So these positions are actually supported by this carbon group right here. So I'm just going to pick this position right here, and put the sulfur trioxide there. So our product will look like our first benzene ring here with nothing on it, and our second benzene ring with our ether and our sulfur trioxide there. So now it's a sulfate group with the OH. Now, we've been adding bromines, nitrates, and sulfur trioxides, but we haven't added any alkyl groups like a methyl or ethyl or propyl. So what if we want to do that? Well, to do that, we have to do something called Friedelcrafts alkylation. So how does that work? Well, you have your ethyl group right here, and you have a chlorine, and we have aluminum chloride. And what this aluminum chloride is going to do is form a carbocation on this carbon with the chlorine. And so now it'll just act like an electrophile, just like in every other situation. And we'll go to the positions that supported the most. So in this situation, it will be the ortho position for this methyl, or the pair position. So I'm just going to draw the ortho product. And so what we're going to have is our benzene ring with our methyl group, and we will have our ethyl group forming over there. Plus, and I'll write plus para product over here. Now, the larger the group gets, the more likely we're going to go para. So, just to show you what it looks like, here's the para product as well. So, that's our ortho, that's our para. Now, in this situation over here, we have a tert-butyl group. Now, what's different between a tert-butyl and a methyl? Well, tert-butyl is pretty big. So, even though it is ortho and para directing because it's electron donating, we're going to pick the para position because we want to avoid as much steric hindrance as possible. Remember, the bigger the group, the more likely we want to go para. So our final product will look something like this with our tert-butyl at the top, and we'll have our ethyl at the bottom. Now, in this third example, we have a propyl with a chlorine on it. Now, what's the difference between ethyl with a chlorine and propyl with a chlorine? Well, the thing is that even though we have a carbocation on that carbon right there, that's a primary carbocation. And what happens if we do a methyl shift or a hydride shift right here? If we do a hydride shift, we end up having a carbocation on a secondary carbon. So what is that? That's a rearrangement. So what ends up happening is that we no longer have a propyl group being attached to the benzene ring. Instead of a propyl group attaching, we have a isopropyl group. So I'm going to draw the para product. So now we have an isopropyl group. That's not what we wanted to add. We wanted to add a propyl group. So how do we do that? How do we add just a propyl group without having rearrangements? Well, we have a new type of reaction called Friedelcrafts acylation. And you have an acyl group or an acid chloride group essentially. So if you have this carbon that's connected to a double bonded to an oxygen and a chlorine, and you add aluminum chloride, you're going to form a carbocation there by having the chlorine go away. So this chlorine will go and you'll form a carbocation right there. And it'll essentially just attack this benzene ring like it would attack anything else. And it will form this group right here. So it'll look something like this with our double bond to the oxygen right there. So we have our 3-carbon group right there being attached with a double bond to the oxygen. Now in this next example, it's the same thing, Friedelcrafts acylation. And I'm just going to incorporate the ideas of activated and deactivated rings. And so in this situation, which of these rings is activated? Well, they're both connected to this ester, but they're connected in different sides. So on this benzene ring, it's connected to the side of the carbon that has a double bond to the oxygen. Now this carbon right here has a partial positive charge because of this double bond to the oxygen. So this ring is actually deactivated, and that's because it has an electron withdrawing group right here. While over here on this benzene ring, it's connected to an oxygen directly. That's very similar to the ethers that we've been seeing recently. So this ring is actually activated. So we're just going to pick the ortho or the para positions for this ether. And we don't have any other stronger electron donator groups. The only stronger donator group that we can possibly think of is an oxygen with a negative charge, and we don't have that here. So the ortho and the para positions are these two positions. And so we're just going to pick the para positions to avoid steric hindrance. And our product will look something like this. We have our first benzene ring. We have our second benzene ring, which has nothing on it. We did not add any groups to it. And we have our ring right there. And we're simply going to add the acyl group, or the acid chloride group, over on the para position. So it looks something like this. And so that's a bunch of electrophilic addition reactions that we've seen. But there's more to it than just electrophilic additions. We can even have nucleophilic substitutions, which is really interesting. So what does that look like? Well, nucleophilic substitution is pretty simple. You're going to have an electron withdrawing group like this, like so. So a nitrate group is an electron withdrawing group. You're going to have a leaving group like a halogen. What ends up happening is that one of the pi bonds in this benzene ring forms a negative lone pair under the nitrate group, and so we have a positive charge under the halogen, and essentially the nucleophile will just go and attack that carbon with a positive charge, and the leaving group will leave afterwards. And so our final product will look something like this, where we still have our electron withdrawing group intact. However, the leaving group leaves, and our new group is our nucleophile, so NH2 in this situation. Now, over here, we have the same situation, but now we have two leaving groups. And which one do we do? Well, one thing you have to realize about nucleophilic substitution is that electron withdrawing groups are no longer meta-directing or meta-allowing. In electrophilic additions, like we had previously, they were meta-directing, meta-allowing, because those were the more stable situations. However, in this situation, they're ortho and pair directing. If you notice, this fluorine was ortho to the nitrate. That's exactly the difference between nucleophilic substitutions and electrophilic addition. That ortho and paired positions are more preferred when you have an electron withdrawing group. So the ortho and pair positions in this situation are these positions. So guess what? Even though bromine's a better leaving group, fluorine is going to be the one that's going to leave, because we're going to form a positive charge on the pair position when we have our negative charge on the under the nitrate. And so our product will look something like this, with the bromine not changed, the nitrate still there, and the fluorine has left, and we have now the amine. So that's nucleophilic substitutions. Now, what about reduction and oxidation reactions? Can't we do that? Is that even possible in benzene rings? Well, yeah, that is possible. So the first type of reduction we can have is for our nitrate group. See this nitrate group right here? We can actually change it into an amine. How do we do that? If we add a catalyst like zinc or iron with dilute hydrochloric acid, we end up getting this product right here, which is just the benzene ring, but now we no longer have a nitrate group. We have an amine. So that's what nitrate looks like when it's reduced using these reagents. Now, what about the acyl group? Remember, we added the propyl group with the double bond to the oxygen. But what if we want to get rid of that double bond to oxygen? We just wanted just the methyl groups, just the carbons and the hydrogens. That's all we wanted. Well, we can have two ways of reducing it. One way is using amalgamated zinc, which is zinc with mercury, and dilute hydrochloric acid. Or we can use hydrazine, which is NH2NH2, and warm potassium hydroxide, so a strong base with heat. And this will just give us this product right here. Well, we have our benzene ring still intact, but now we no longer have this double bond in oxygen. Instead, we have two hydrogens that are replaced with it. And that's it. Now, what about this third reduction reaction? It's something called the Birch reduction. Yeah, and I forgot to mention, this right here is the Clemmensen reduction. So that's what it's called. Now, this one right here is called the Birch reduction. And how do we do it? Well, with the Birch reduction, essentially what happens is that you'll get a product that only has two pi bonds. So I'm going to draw it like this, and I'm going to draw the Birch reduction benzene ring, which is no longer a benzene ring, for the other one as well. Now, how do we know where the methyl and the nitrate group are positioned? Well, if you have an electron withdrawing group, it's going to be positioned in between the pi bonds. And that just has to do with the mechanism that you may want to look at, but that's all you have to know is that electron withdrawing groups will be in between the two pi bonds, while electron donating groups, like a methyl, will be on the carbon with the pi bond. And so that's all there is to it with the Birch reduction. And the reagents are simply sodium or lithium and liquid ammonia and some sort of alcohol. So ethanol, methanol, those are alcohols groups. That helps the Birch reduction happen. Now, if we can reduce stuff, we can also oxidize it. Now, if you have potassium permanganate and warm sodium hydroxide, what's going to happen is that this potassium permanganate is going to look for any benzylic hydrogens. So if you have a hydrogen right here, that's a benzene hydrogen, and we don't want that. We want benzylic ones. So a benzylic hydrogen is like one on this carbon right here. And potassium permanganate will essentially, if it finds one like this, what it will do is basically cut off any ties this carbon has to anything else other than that hydrogen, and it will form this product right here. It will still have the benzene ring intact. It will not cut any of these double bonds like we've seen in like earlier chapters. It will keep it intact, and what will happen is that this carbon group, instead of having whatever group it has on it, will now have a double bond to an oxygen and an OH group. So now it's a benzoic group, or benzylic acid group. So that's what that looks like. Now in this situation, we have the same thing again, where we have a benzylic hydrogen over here, but over here on this tert-butyl group, we have no benzylic hydrogen, so no H. So no benzylic hydrogens over here. So potassium permanganate can grab onto this. It can do that, but there's no hydrogens over here for it to grab onto. So the product will simply just be the benzene ring. Again, the tert-butyl group will literally not change because it has no benzylic hydrogens. However, the methyl group will change and it'll form a double bond to an oxygen and then a single bond to an OH. So that's the type of reactions we've seen so far. Now those are usually the most important reactions we will see in aromatic reactions, but there are some extra ones that you might just want to know, and they're pretty easy to know. So we have something called organometallic coupling. We essentially just couple a group with the benzene. So in this situation, if you have any group like this with a copper and lithium group on it, essentially take this right here and bond it to the carbon that has a leaving group like iodine, and your product will simply just look like this with the benzene group still intact, and it will be attached to that group that we saw earlier, that 2-carbon group with a double bond. And in this next situation, if you have the proper reagents, well, essentially what will happen is that we'll have this entire group right here just be attached to this carbon. So we have our benzene ring. Again, it's still intact, it doesn't change, but now it's attached to that group that we saw with the OCH3 and the double bond to the oxygen. That's all there is to it. And with this third one, what we just do is we just take out that boron and we just connect this group right here and connect it to the group with the leaving group. And OH right here is not a leaving group, but the bromine is. And so our reaction will look something like this. The product will have the OH still intact, our benzene ring still intact, and our new group is a new benzene ring. And so that's all there is to it. Now the last two reactions are these two right here. So if you add chlorine under high heat and pressure, you'll simply just get a cyclohexane, right? And this cyclohexane, what's special about it is that you'll have chlorine on all carbons. And that's all there is to it. So you lose all of your double bonds. And if you do the same thing with hydrogen gas with some sort of catalyst, high heat, or rubidium catalyst, high heat and high pressure, you'll get the same thing. You'll get a cyclohexane, but instead of chlorines being added onto it, it's just simply hydrogens being added. And that's all there is to benzene aromatic reactions. So I'm going to zoom out. We're going to see all the reactions we've done so far. So just to review, the reactions we've gone over so far are the following. We have our electrophilic additions, which with bromines and some sort of catalyst. We have our mononitration. We have our sulfonation. We have our alkylation with a regular donating group, a large group which forces to go para, or a rearrangement with our alkylation. We have our Friedelcrafts acylation, which has the acid chloride, and another Friedelcrafts acylation that I've shown here. Then we have our nucleophilic substitution, and we know that electron drawing groups, instead of being meta-directing, now they're ortho and para-directing. And then we have our reduction group, so we just have reduction of a nitrate group. We have our Clemmensen reduction, which changes an acyl group to just a regular propyl ethyl methyl alkyl group. And then we have our Birch reduction, which changes our benzene ring to just a cycloalkene with 2 pi bonds, with the electron withdrawing group in between the pi bonds and electron donating group on the carbon with the pi bonds. And then we have oxidation, where potassium permanganate essentially looks for benzylic hydrogens and forms a carboxylic acid over there. And then we have our organometallic coupling, where we essentially just couple the groups that we've seen as long as we have our proper reagents with just the carbon that has a leaving group on it. And then if we put high pressure and heat, we can add chlorine on all the carbon bonds, or we can add hydrogen on all the carbon bonds and get rid of the pi bonds within the benzene group. And that's all there is to aromatic reactions. I hope you enjoyed